Number 1. Kolumbo. 7 kilometers northeast of Santorini, the seafloor opens into a crater 3 kilometers wide. The rim sits 18 meters below the surface. The floor drops to 500 meters. This is Kolumbo, and according to a study published in 2023, its magma chamber is currently swelling. Evie Nomikou of the University of Athens and Michel Pilato of Imperial College London used seismic tomography to image a melt body 2 to 4 kilometers beneath the crater floor. The chamber holds 1.4 cubic kilometers of liquid magma. It is inflating at a rate of approximately 4 million cubic meters per year. Their conclusion was deliberately understated. They wrote that an eruption could occur in our lifetime. To understand what that means, you have to look at the last time Kolumbo erupted. In 1650, a column of gas, ash, and steam burst from the sea above the crater. A tsunami struck the western coast of Santorini. A pyroclastic surge swept across the water at the speed of a freight train. Approximately 70 people died on Santorini and Ios, primarily from suffocating gas clouds that moved with the prevailing winds. The eruption magnitude was a volcanic explosivity index 6, comparable to the 1991 Pinatubo event, and significantly larger than Mount St. Helens in 1980. Kolumbo sits on the Hellenic subduction zone, where the African tectonic plate descends beneath the Aegean microplate at 3.5 centimeters per year. The volcano is not alone. 20 additional submarine cones have been identified along the Santorini-Kolumbo line, suggesting an extended volcanic field rather than a single isolated edifice. The crater itself is biologically active. Continuous carbon dioxide venting through the floor maintains fluid temperatures up to 220 degrees Celsius. The acidified pool drops as low as pH 5. Inside this chemistry, extremophile microbes thrive. Persephoneella and Thiomicrospira species harvest energy from the volcano's exhalations. The most unsettling part of the 2023 finding is not what was seen, it is what was confirmed about how Kolumbo and Santorini connect. Pilato's team showed that the two volcanic systems draw from separate magma chambers. This means Santorini's monitoring network, which is dense and modern, may not detect a precursor to a Kolumbo eruption. The Hellenic Volcano Monitoring Center installed ocean bottom seismometers above Kolumbo in 2022. The Greek Civil Protection Agency upgraded the volcano's threat classification after the 2023 paper. Evacuation protocols for Santorini's cruise terminal are under review. Tsunami modeling by Tinti and colleagues suggests that a Kolumbo eruption could send 2 to 4 meter waves to the surrounding islands within 10 to 20 minutes. Approximately 1.5 million tourists visit Santorini every year. The closest cruise ship anchorages sit directly above the most active vent field. The mainstream view among Greek volcanologists is that Kolumbo's activity is increasing on a timescale of decades to centuries, not hours. The competing archaeological view holds that the volcano has been continuously dangerous since the Minoan eruption nearly 4,000 years ago, and that the 1650 event was simply the most recent in an ongoing pattern. A more speculative interpretation, advanced by a handful of researchers, suggests that the Santorini caldera and Kolumbo may interact through deeper, undetected pathways, which would mean any eruption of one could destabilize the other. The crater is monitored, the chamber is swelling, to water if the chamber is filling. The fundamental question which Nomikou and her colleagues raised openly is no longer whether Kolumbo will erupt. It is when, and whether anyone will be able to evacuate Santorini in time. Number 2. Fani Maoré. In May of 2018, the island of Mayotte began to shake, not with one earthquake, but with thousands. Over the next 12 months, French monitoring stations recorded more than 30,000 seismic events under the island. Residents felt a magnitude 5.9 quake. The shaking was unexplained. Mayotte sits roughly halfway between Madagascar and the African mainland, far from any major fault line known at the time. Then the island started to move. GPS networks designed to track ordinary tectonic motion showed Mayotte sinking. It dropped 20 centimeters in a single year. It shifted 24 centimeters eastward over the same period. Geophysicist Nathalie Feuillet at the Institut de Physique du Globe de Paris led the team that began searching for an explanation. In May of 2019, the French research vessel Marion Dufresne arrived east of the island with the multibeam sonar. What they found rewrote the regional tectonic map. 50 kilometers east of Mayotte, sitting on a seafloor 3,500 meters deep, a new mountain had grown out of the abyss. It stood 820 meters tall. It measured 5 kilometers across at the base. It had not been there before. The volcano was given the name Fani Maoré, which in Shimorian means the depths of Mayotte. It was, and remains, the largest underwater volcanic eruption ever recorded in human history. The total volume of erupted lava was 6.5 cubic kilometers, comparable to Iceland's 2014 Bunga eruption. At peak intensity, magma was emerging at 180 cubic meters per second. The magma came from an exceptionally deep reservoir, between 30 and 50 kilometers below the seafloor. This depth is among the deepest documented for any eruption in modern times. The lava chemistry was basanite, rich in mantle-derived volatiles. The eruption released approximately 30 megatons of carbon dioxide directly into the deep ocean. To put that in perspective, that single underwater event injected more carbon dioxide into the ocean in 1 year than most decades of explosive aerial volcanism combined. What makes Fani Maoré genuinely disturbing is not its scale. It is the fact that it remained invisible. No fishermen reported anything. No ships saw a plume. Surface satellite imagery showed nothing. The volcano was detected only because the entire island of Mayotte tilted. The discovery came indirectly through GRACE follow-on satellite gravimetry in 2019, which picked up changes in seafloor mass. 290,000 people live on Mayotte. They felt the earthquakes for months without anyone being able to tell them why. The mainstream geophysical interpretation is that Fani Maoré marks the activation of a new branch of the East African Rift System, extending southward into the Comoros Basin. A competing interpretation, advanced by Anne Lemoyne in a 2023 Nature Geoscience paper, describes the Western Indian Ocean mantle as anomalously productive. The fringe interpretation goes further, suggesting that the Comoros region may be a previously unrecognized hotspot, potentially the southernmost expression of a deep mantle plume. As of late 2025, Fani Maoré is still considered an ongoing eruption at reduced intensity. The Rivasima Observatory Network, installed by the French government in 2019, monitors continuously. The implication is unsettling on a global scale. If a continent-scale volcanic eruption could happen unobserved for over a year off the coast of an inhabited French territory, the question is no longer how many submarine eruptions are happening right now. The question is how many we have failed to notice. Number 3. Brimstone Pit. 100 kilometers north of Rota Island in the northern Mariana Islands, a submarine volcano summit rises to 517 meters depth. Its base extends down to 2,700 meters. This is NW Rota 1. In March of 2004, a NOAA expedition called Submarine Ring of Fire was conducting routine bathymetric surveys when its remotely operated vehicle, Jason Onnesengen, descended toward the volcano's summit. What it found became the most important discovery in deep-sea volcanology of the 21st century. NW Rota 1 was erupting right then, on camera. It has been erupting ever since. Every year since 2004, ROVs sent to the volcano have recorded ongoing eruptive activity. NW Rota 1 is the world's first continuously documented underwater eruption, and it remains the longest-running natural laboratory for studying how submarine eruptions actually work. The active vent is called Brimstone Pit. From the seafloor, molten sulfur emerges in glowing yellow balloons, some as large as 2 meters across. They rise slowly through the water, expand under reduced pressure, and burst, releasing droplets of liquid sulfur that drift like rain. The temperature at the vent has been measured at over 600 degrees Celsius in the hydrothermal fluids. The magma itself, inferred from chemistry, sits at 1,100 to 1,200 degrees Celsius. The lava type is bonanite, a silica-rich, water-bearing magma associated with the initiation of subduction zones. It is the kind of lava that, on land, exists only in 2-billion-year-old rocks. Bill Chadwick of NUA and Oregon State University has led research at Brimstone Pit since the discovery. His team has documented explosive bursts of carbon dioxide-rich gas occurring every few seconds. Hydrophones can detect the rumbles from 30 kilometers away. Native sulfur stalactites grow from the chimney mouths. Barite crystals precipitate around the vent. Microbial mats dominated by epsilon proteobacteria oxidize sulfur as an electron donor, building the chemical foundation that supports a unique ecosystem. At the center of that ecosystem is a vent shrimp called Opapalae loihi. The shrimp do not depend on plankton from the surface. They feed by scraping bacterial mats directly off the volcano's rocks. The bacteria use sulfur and carbon dioxide from the eruption itself as their energy source. The shrimp populations crash with each eruptive pulse and then recover as the chemistry stabilizes. Evolution is happening in real time, on a single volcano, under continuous observation. In 2009, the Jason the Tainu ROV captured high-definition video of molten lava extruding underwater. It was the first such footage ever recorded. In 2014, a separate expedition recorded the largest sulfur balloon ever documented at the volcano, 2.5 meters in diameter, drifting 50 meters before bursting. In 2018, the Schmidt Ocean Institute mapped a second vent field 200 meters from Brimstone Pit, suggesting that the magma system is larger and more complex than originally thought. Ken Rubin of the University of Hawaii used radiometric dating in 2010 to confirm that the volcano has been continuously active for at least the last 5 years and likely decades, and possibly much longer. The mainstream interpretation is that NW Rota 1 is a steady-state subduction zone volcano with a continuously replenishing magma supply. A competing view holds that the volcano is in a pre-paroxysmal phase, slowly building toward a larger eruption that has not yet arrived. The most speculative interpretation, raised by a small number of geochemists, is that Brimstone Pit may be representative of a much larger population of continuously erupting volcanoes that we simply have not yet found. Number 4. Kikumjeni. 8 kilometers north of Grenada, in the Lesser Antilles volcanic arc, a submarine volcano summit sits 180 meters below the surface. Its base extends to 1,300 meters. Its name comes from local fishing legend, which described the kicking turbulence of vessels passing over the active vent. The legend was right. The vessels were kicked by volcanic gas plumes rising through the water. This is Kikumjeni, and it is the only submarine volcano in the world with a permanent maritime exclusion zone enforced by a national coast guard. The exclusion zone is 1.5 kilometers in radius during normal activity. It expands to 5 kilometers during alert. The Grenada Coast Guard enforces the zone in coordination with regional maritime partners. The alert level system runs from green through yellow, orange, and red. A red alert triggers automatic enforcement of the expanded zone. This is not a precautionary fiction. Kikumjeni has erupted at least 13 documented times since 1939, when the first surface eruption was witnessed. In 1939, residents of Grenada watched a 270-meter-high column of water and steam burst out of the sea. The volcano's summit, then much deeper than today, had moved closer to the surface through accumulated eruptive products. Repeated bathymetric surveys over the following decades have measured a consistent vertical growth rate. The summit is rising approximately 4 meters closer to the surface every decade. At the current rate, the summit could breach the photic zone within several human generations and become a new Caribbean island. The most recent confirmed eruption occurred in April of 2017. The volcano emitted continuous degassing of carbon dioxide and hydrogen sulfide, producing visible watercolor changes at the surface. Seismicity increased. Maritime traffic was rerouted. Monitoring is conducted by the Seismic Research Center at the University of the West Indies in Trinidad. A 2019 ROV expedition discovered a new submarine cone 700 meters from the main vent, indicating that magma is migrating laterally. The magma source is approximately 100 kilometers deep, drawn from the subducted North American plate beneath the Caribbean. It feeds the same broader magmatic system that produces the Soufriere Hills volcano on Montserrat. The tsunami risk is the primary hazard. Jacqueline Kaplan-Auerbach of Western Washington University published modeling in 2016 suggesting that a Plinian-style eruption could occur once Kikumjeni's summit nears the photic zone. A flank collapse could produce a regional tsunami affecting Grenada, the Grenadines, Trinidad, Tobago, and the northern coast of Venezuela. Frederick Dondan's 2018 analysis went further, proposing Kikumjeni as the most hazardous volcano in the Lesser Antilles arc. The implication for tourist economies is direct. 6 island nations sit within potential wave arrival zones. The vent field hosts the only known Caribbean population of chemosynthetic tube worms, Lamellibrachii barhami. They live in dense mats around the active fluid emissions, fed by sulfide oxidizing bacteria. The mainstream interpretation of Kikumjeni's behavior is that it is in a steady eruptive phase characteristic of young arc volcanoes. The historical interpretation drawn from older fishermen accounts suggests that activity has been continuous since at least the late 1700s. The fringe view, less well supported, is that Kikumjeni may be undergoing magma chamber consolidation that could produce a much larger eruption within decades. Number 5. Marsili. In the southern Tyrrhenian Sea, 140 kilometers north of Sicily and 175 kilometers southwest of Naples, the largest volcano in Europe sits underwater. It is 3,000 meters tall. It is 70 kilometers long. It is 30 kilometers wide. Its summit sits 450 meters below sea level. It is named for Italian geographer Luigi Ferdinando Marsili. Most Italians have never heard of it. This is Marsili Seamount. It dwarfs every other volcano in Europe, including Etna and Vesuvius. It formed during the opening of the Tyrrhenian back arc basin, beginning approximately 700,000 years ago. The volcano sits behind the Calabrian subduction zone, in a region where the African plate is being pulled apart by the larger forces driving the Mediterranean's tectonic puzzle. The last confirmed eruption is estimated to have occurred between 2,100 and 5,000 years ago, well within geological recency. In 2010, Enzo Boschi and colleagues at the Istituto Nazionale di Geofisica e Vulcanologia published a study warning that Marsili remains active. Their analysis indicated that the volcano could erupt again, and more significantly, that a flank collapse could trigger a tsunami affecting the Italian coast within 30 minutes. In 2014, Stefano Tinti of the University of Bologna modeled the wave dynamics in detail. His simulation suggested that a major collapse could produce 2 to 4 meter waves along southern Italy's coast. Approximately 8 million people live within potential tsunami impact zones along the Tyrrhenian. The active hydrothermal system at the summit has been documented by Italian Coast Guard expeditions since 2006. A 2017 ROV expedition recorded black smoker chimneys up to 50 meters tall on the summit. The magma chamber sits 8 to 10 kilometers below the seafloor, with a melt volume estimated at 1.5 cubic kilometers. Roberto Sabadini led a high-resolution seismic survey in 2018 that imaged the magma reservoir, interpreting it as currently active. Guido Ventura's 2020 paper found evidence of fluid-driven seismicity at depth consistent with ongoing magma migration. The flank collapse hazard concentrates on the northeast side of the volcano, where the slope is steepest and the sediment cover thinnest. Marsili is part of a chain that includes the smaller Vavilov, Magnaghi, and Palinuro seamounts, collectively defining the back arc spreading axis. The mainstream Italian volcanological view is that Marsili poses a moderate long timescale hazard. The historical seafarers' view, drawn from older Mediterranean maritime records, suggests that anomalies in the southern Tyrrhenian have been noted for centuries, though never directly attributed. The more speculative view, advanced by a minority of researchers, is that the volcano is structurally compromised in ways the current monitoring cannot yet detect, and that the flank collapse risk is higher than the official assessment. In 2010, Italy's Civil Protection Department added Marsili to its national volcanic hazard map alongside Etna and Vesuvius. The volcano is too deep to produce a Plinian eruption column reaching the atmosphere. But a sudden caldera collapse remains the primary concern. The depth of the summit, the steepness of the flanks, and the proximity to a populated coastline combine into a geometric risk that does not require an explosive eruption to be catastrophic. Marsili does not need to erupt to be dangerous. It only needs to slip. Number 6. West Mata. In May of 2009, 200 kilometers southwest of Samoa, an ROV called Jason the Kenk descended into the northeast Lau Basin. The water was black. The instruments registered a deep volcano at 1,165 meters depth. As the ROV approached the summit, its lights caught something that no human had ever seen on camera. The volcano was erupting. Pillows of glowing red lava were emerging from a vent on the seafloor. The lava was meeting seawater. The interaction was producing sharp popping sounds clearly audible on the hydrophone. Bill Chadwick of Niue Ken Rubin of the University of Hawaii and Joseph Ressing as expedition lead were watching the first deep-sea volcanic eruption ever captured on video. The volcano is called West Mata. It sits 2,800 meters from base to summit on the Tonga Kermadec subduction zone, where the Pacific Plate descends beneath the Australian Plate at a rate of approximately 24 centimeters per year. This convergence rate is among the fastest on Earth, faster than the rate at which fingernails grow. The eruption produced rare bonanite lava, a high magnesium, high silica magma previously known mainly from ancient rocks, dated to approximately 2 billion years old, in places like the Bonin Islands south of Japan. The name bonanite comes from those islands. West Mata's bonanite production gives geologists a living analog for one of the most important and least understood processes in plate tectonics, the initiation of a subduction zone. Bonanite chemistry forms only when fluids and melts interact under specific conditions found at the earliest stages of one plate, beginning to dive beneath another. To watch West Mata erupt is, in geochemical terms, to watch the early Earth. The eruption temperatures exceeded 1,200 degrees Celsius. Lava-water interaction produced thick sulfur deposits, native sulfur ponds, and acidic hydrothermal plumes that spread across the Lau Basin. A 2011 paper in Nature Geoscience formalized the discovery. The authors described West Mata as the deepest deep-sea eruption ever directly observed and the first explosive deep eruption ever filmed. A follow-up expedition in 2011 documented dense communities of vent-adapted shrimp and limpets that had colonized the new lava within 18 months. The vent field also hosts the deepest known population of Pyrolobus archaea, microorganisms that can survive temperatures up to 113 degrees Celsius. The eruption is intermittent. Confirmed activity occurred in 2008, 2009, and 2010, followed by a quieter phase, then renewed activity detected by hydroacoustic monitoring in 2017. David Clegg of the Monterey Bay Aquarium Research Institute published a 2018 study analyzing eruptive products from West Mata. His team identified pulsed magma chamber recharge events that drive distinct eruptive episodes separated by months to years. Bonanite lava production averages approximately 5 million cubic meters per year during active periods. In 2020, an expedition discovered a new lava field southwest of the main vent, suggesting ongoing magma migration. West Mata remains the most accessible deep bonanitic system on Earth. The mainstream geochemical view is that West Mata represents the modern initiation of a new subduction segment in the Lau Basin. A competing view, advanced by some structural geologists, holds that the volcano is a relic of older subduction processes that have been geochemically preserved by the unique back arc setting. The more speculative interpretation, raised by a minority of researchers, is that bonanite production may be far more common in deep submarine settings than land-based geology has ever suggested, and that the rocks we call ancient may simply be the small fraction that survived erosion. Number 7. Monowai. 1,100 kilometers north-northeast of New Zealand in the Kermadec Arc, a submarine volcano summit rises to between 100 and 150 meters depth. Its base extends to 1,500 meters. It is named for a New Zealand naval research vessel that surveyed the area in the 1940s. The vessel's crew did not know they were charting one of the most frequently active submarine volcanoes on Earth. Documented eruptions at Monowai Seamount have occurred in 1944, 1977, 1980, 1986, 1988, 2002, 2005, 2007, 2008, 2011, and 2014. In May of 2011, between the 14th and the 17th, Monowai produced one of the most precisely recorded submarine eruptions in history. The International Monitoring System hydrophone arrays operated by the Comprehensive Nuclear Test Ban Treaty Organization picked up the eruption signals. Acoustic energy from Monowai was detected at hydrophone stations more than 8,000 kilometers away in the Indian Ocean. The eruption itself was extraordinarily dynamic. Multi-beam bathymetric surveys conducted before and after the event, analyzed by Richard Y. Sosansky at NIWA in 2012, showed that the volcano's summit grew approximately 72 meters in 5 days. Then, in a single afternoon, the summit partially collapsed. 9 million cubic meters of new volcanic material were produced in less than a week. That is roughly the volume of 3,600 Olympic swimming pools, created by a single submarine eruption that almost no one noticed at the surface. The eruption chemistry was basalt to basaltic andesite, with the subduction zone fluid signatures characteristic of the Kermadec arc. Yellow-green water discoloration events visible from satellite have been recorded at Monowai going back to the 1940s. The 2014 eruption produced a phreatic explosion that briefly breached the sea surface, ejecting a steam cloud visible from passing aircraft. Susan Merle of NOAA published a 2016 paper demonstrating that Monowai's eruption frequency correlates with seismic activity along the Kermadec subduction zone. When stress accumulates along the subducting Pacific plate, magma pathways open in the overlying mantle wedge, and Monowai responds. The vent field hosts the deepest documented population of stalked barnacles in the southern Pacific. Local hydrothermal plumes have been detected at distances of over 50 kilometers from the vent. The volcano sits in international waters but falls within New Zealand's hazard monitoring network. The summit emergence projection is one of the most interesting open questions in submarine volcanology. At current growth rates, Monowai could break the surface within 50 to 200 years, creating a new island in the southwest Pacific. The mainstream view is that this emergence will happen on a slow, century-scale timeline. A competing view drawn from the 2011 event's rapid construction holds that emergence could occur much faster, possibly in a single dramatic eruption sequence. The fringe view, less well supported, is that the volcano is approaching a structural threshold and could produce a major caldera-forming event before the summit ever reaches the surface. Monowai is now the global reference target for submarine eruption detection algorithms. The acoustic signatures from its eruptions are used to calibrate detection systems worldwide. Every time it erupts, our ability to detect the next submarine eruption anywhere on Earth improves slightly. Number 8. Hunga Tonga. On January 15, 2022, 65 kilometers north of Tonga Tapu, a submarine caldera erupted. The eruption produced the most powerful atmospheric explosion measured on Earth since the 1883 Krakatoa event. Approximately 10 cubic kilometers of material were ejected. The plume rose to 57 kilometers altitude, the highest volcanic plume ever recorded. The eruption injected 150 megatons of water vapor into the stratosphere, equivalent to about 10% of the entire stratospheric water budget. The atmospheric pressure wave circled the Earth 4 times and was detected at every barometric station on the planet. The seismic equivalent magnitude was 5.8. Hydrophones recorded the explosion 18,000 kilometers away. The infrasound was audible in Alaska, 9,400 kilometers from the source. This was Hunga Tonga Hunga Ha'apais, a submarine caldera volcano with a pre-eruption summit at 114 meters depth and a caldera roughly 5 kilometers in diameter. The volcano had erupted modestly in 2009 and again between 2014 and 2015, when activity briefly built a temporary land bridge between two small surface islands. The January 2022 event was different. Shane Cronin of the University of Auckland led the analysis that characterized it as a Frida-Plinian eruption, the result of extreme magma-water interaction at shallow depth. 2 cubic kilometers of magma intruded into seawater in less than 90 minutes. That is the fastest documented magma-water interaction in the modern geological record. The caldera collapse removed approximately 8 cubic kilometers of edifice rock. The seafloor inside the caldera dropped by up to 700 meters in a single event. The tsunamis generated by the eruption reached as far as Peru, where 2 people drowned, and Japan, with run-up exceeding 1.5 meters at multiple locations. A 2023 paper in Science by Sam Purkis at the University of Miami documented submarine pyroclastic density currents traveling at speeds up to 122 kilometers per hour for distances of over 80 kilometers from the vent. These flows severed all the undersea fiber optic cables linking Tonga to the global internet for over a month. 6 people died in Tonga from the eruption and its tsunamis. Damage exceeded $90 million United States dollars. The event was the largest atmospheric explosion ever directly observed by modern satellites. NASA, NOAA, JAXA, and European Space Agency instruments captured the eruption in unprecedented detail. The stratospheric water vapor injection is expected to cause a small global warming effect of approximately 0.035 degrees Celsius over the 5 years following the event. This makes Hunga Tonga the only volcanic eruption in modern times, measured to warm rather than cool the planet. The volcano is currently rebuilding underwater. Bathymetric surveys conducted in 2023 and 2024 show magma reaccumulation in the central vent. Marco Brenna of the University of Otago published a 2024 paper detecting fresh degassing signatures and suggesting that Hunga Tonga could re-enter eruptive activity within 5 to 20 years. Tongan civil defense maintains permanent monitoring of the volcano via seismic and gas sensors supplied by New Zealand and installed shortly after the 2022 event. The mainstream view is that another major eruption is unlikely on a short timescale, given the recency of caldera collapse. A competing view, drawn from comparison with other Freda-Plinian volcanoes, suggests that magma chamber recharge could occur faster than mainstream models predict. The more speculative interpretation, raised by a small number of researchers, holds that the 2022 event may have permanently destabilized the regional volcanic system, with implications for nearby submarine volcanoes along the entire Tonga-Kermadec arc. Watching a submarine volcano is fundamentally an inferential exercise. You cannot see the volcano. You cannot stand on it. You cannot smell the gas. Everything we know about active deep eruptions comes from indirect signals captured by an unevenly distributed network of sensors. Multi-beam sonar bathymetry produces high-resolution maps of the seafloor, and repeat surveys reveal eruption-driven changes. When a summit grows or collapses, sonar catches it. The International Monitoring System Hydroacoustic Network, originally designed to detect underwater nuclear weapons tests, has become the most sensitive submarine eruption detector on Earth. Sound from a deep volcano can travel in the SOFAR channel for 10,000 kilometers or more, allowing detection from a single station on the opposite side of the planet. Ocean bottom seismometers are the workhorses of submarine volcanism monitoring. They sit on the seafloor, often for years, recording vibrations from magma movement and eruption. The GRACE follow-on satellite mission detects mass changes from seafloor deformation, which is how Fani Maoré was confirmed. GPS networks measuring island deformation can serve as proxies for nearby submarine activity. Magnetotelluric surveys image magma chambers electrically. Argo float networks detect eruption-driven temperature anomalies in the deep ocean. ROV technology has evolved from the tethered submersibles of the 1970s to today's autonomous vehicles, which can survey volcanoes without a surface ship overhead. Pumice rafts visible from satellite are eruption signatures from above. Hydrothermal plumes are detected by nephelometry, the optical fingerprint of suspended particles. Chemical signatures such as helium-3, methane, manganese, and iron anomalies confirm volcanic origin. NOAA's Pacific Marine Environmental Laboratory coordinates much of this work with global partners. The Schmidt Ocean Institute's open data model has accelerated the field substantially. The cost gap is real. Monitoring a single submarine volcano costs more than monitoring 100 land volcanoes. Most submarine volcanoes in international waters fall into a political gap with no clear monitoring authority. Even with all these tools, the forecast horizon for an eruption remains years for magma chamber inflation, but only hours for the eruption itself. Pressure changes everything. Every 10 meters of depth adds 1 atmosphere of pressure. At 1,000 meters, the pressure is roughly 100 times surface. At 3,000 meters, it is 300 times surface. This pressure suppresses the explosive release of dissolved gases from magma. The transition depth is approximately 500 meters. Below this, most volatiles stay dissolved in the lava, and eruptions tend to be effusive rather than explosive. Above this, shallow submarine eruptions can become phreatomagmatic, producing the kind of catastrophic interaction seen at Hunga Tonga in 2022. Pillow lava is the signature texture of underwater eruption. The molten lava forms rounded lobes as it cools rapidly against seawater. The chemistry of submarine eruptions ranges from bonanite to basanite, basalt, andesite, and rhyolite, with each composition telling a different tectonic story. Hydrothermal vent systems often surround active submarine volcanoes, building chemosynthetic ecosystems from the volcano's exhalations. Caldera collapse is the deadliest eruption mode. The acoustic signature of erupting magma includes bubble bursts, brittle fracturing, and slow venting, each producing distinct frequency patterns. Fish and crustaceans flee eruption sites days in advance, responding to chemical and acoustic cues we are only beginning to understand. The local ocean climate near a submarine eruption warms by several degrees, sometimes for years. Submarine volcanism shaped the early atmosphere and may be where life originated. Every submarine volcano is geochemically unique to its tectonic setting. The forecasting difference is dramatic. Land volcanoes typically have hours to weeks of warning. Submarine ones can have seconds. The fundamental humility of the field is that submarine volcanism is the most under-observed major geological process on Earth, even though it represents 75% of all volcanic activity. Across the 8 volcanoes in this video, a single hazard appears repeatedly. The eruption columns are a secondary concern. The tsunami risk is the primary one. Tsunami genesis from a submarine eruption requires sudden vertical seafloor displacement. 3 mechanisms appear consistently across the case studies. The first is flank collapse, modeled at Marsili, Kikumjeni, and Hunga Tonga. The second is caldera collapse, which is what happened at Hunga Tonga in 2022 and which is the primary concern at Kolumbo. The third is the submarine pyroclastic density current, confirmed at Hunga Tonga and theorized at several others. Tsunami arrival times vary dramatically by geometry. Marsili to the Italian coast is approximately 30 minutes. Kolumbo to the surrounding Cyclades is 10 to 20 minutes. Kikumjeni tsunamis would arrive at Grenada within 5 to 10 minutes. Hunga Tonga's 2022 tsunami reached Peru 9,500 kilometers away, where 2 people drowned well outside the predicted impact zone. The Pacific Basin tsunami warning systems missed the Hunga Tonga case because they are calibrated for earthquakes, not for the more complex physics of volcanic tsunamis. The Mediterranean as a closed basin would amplify any tsunami significantly, with resonance and basin geometry shaping wave behavior in ways that simple seismic models do not capture. The Comoros and East African coast remain vulnerable to Fani Maoré despite its great depth. The Lesser Antilles tsunami exposure from Kikumjeni puts 6 island nations at risk. Dirt de buoy networks for real-time tsunami detection have known gaps, particularly in the southern Indian Ocean and the Central Pacific. The 2023 UNESCO Submarine Volcanism Tsunami Working Group is beginning to address these gaps, but the funding remains inadequate for global coverage. The lesson from across the list is consistent. The most dangerous submarine volcanoes are the shallow ones, where summit emergence and flank collapse are both within reach. The 8 volcanoes in this video are not just geological events, they are habitats. Chemosynthesis is the alternative to photosynthesis at these depths. Bacteria and archaea use the volcano's chemical output, primarily sulfur, hydrogen, methane, and iron, as their energy source. Around NW Rota 1, the Opaipali Loihi vent shrimp feed by scraping bacterial mats off the rock. At Kikumjeni, Lamellobrachia barhami tube worms form the only Caribbean population of their kind. At Westmata, Pyrolobus archaea thrive at 113 degrees Celsius, the upper temperature limit of known life. Kolumbo's acidified crater pool hosts Persephoneella and Theomicrospira species. Monowai seamount supports the deepest documented stalked barnacles in the southern Pacific. The epsilon proteobacteria mats are foundational. They oxidize sulfur, fix carbon, and build the chemical platform that more complex life requires. At submarine volcanoes, ecosystems experience boom and bust cycles tied to eruptive pulses. The 18-month colonization timeline at West Medi after the 2009 eruption is now the textbook example of how fast life returns to a sterilized seafloor. After Hunga Tonga's 2022 collapse, the seafloor inside the caldera, dropped by 700 meters, has begun to be recolonized. Vent ecosystems may have seeded all early life on Earth. The 1977 discovery of vents at the Galapagos Rift revolutionized biology by demonstrating that life could exist without sunlight. The pre-photosynthesis world, lasting 3.5 billion years, may have been entirely volcano-fed. The astrobiology connection is direct. Europa and Enceladus, the icy moons of Jupiter and Saturn, may host submarine volcanism beneath their ice shells. If life can exist around an erupting volcano in the absolute dark of an Earth ocean, it can exist around an erupting volcano under the ice of another world. The conservation paradox is real. A single eruption can destroy an endemic ecosystem evolved over millions of years on a single volcano. The same eruption is what created the habitat in the first place. Protecting these habitats means accepting that destruction is part of their continuity. There is a fundamental gap between the data we have and the predictions we need. We cannot reliably forecast the timing of any volcanic eruption. The submarine forecasting gap is at least an order of magnitude worse than the land equivalent. At Kolumbo, the magma chamber is inflating, but we cannot say whether the eruption is decades or centuries away. At Fani Maoré, an entire submarine mountain formed undetected for months. The depth at which routine surveillance becomes impractical is roughly 4,000 meters. Below that, monitoring is occasional and expensive. The data sparsity problem is severe. Approximately 80% of known submarine volcanoes have never been visited by an ROV. The political fragmentation of international waters means many volcanoes fall outside any single nation's hazard monitoring jurisdiction. Most submarine eruption monitoring depends on academic grant funding rather than dedicated infrastructure. The Comprehensive Nuclear Test Ban Treaty Organization Hydroacoustic Network is the best submarine eruption detector in the world, but it is technically a side effect of a nuclear weapons treaty rather than a deliberate volcanology investment. The hazard ranking problem persists. We cannot rank submarine volcanoes by eruption risk in a way that would inform coastal planning. Flank collapse modeling is fundamentally unverified because no model has been tested against an actual large flank collapse event. The total population of active submarine volcanoes is unknown. Estimates range from 10,000 to 100,000 globally. The Mariana Arc is a microcosm. It contains roughly 50 known volcanoes, but only 5 are actively monitored. Climate change is now a factor. Rising sea levels and changing ocean chemistry may be altering submarine volcanic behavior in ways we have not yet modeled. Most past submarine eruptions have been identified only after the fact through chemical or acoustic signatures detected long after the event ended. The honest answer to what we can predict is that we are at the very beginning of being able to predict anything at all. The 8 volcanoes in this video are the documented tip of an iceberg. Recent satellite work, particularly the 2024 SWOT altimetry survey, has revealed tens of thousands of previously uncharted seamounts. There are now at least 1.5 million known seamounts on Earth. An unknown fraction of them are volcanically active. The Reykjanes Ridge eruption field southwest of Iceland was only fully mapped in 2025. The South Sandwich Trench Arc contains multiple submarine volcanoes that have never been studied in detail. The Kerguelen Plateau in the southern Indian Ocean is a possible site of unknown active volcanism. The Lau Basin hides additional vent fields beyond West Mata and Monowai. The Galapagos. Spreading Center's southern extension is poorly mapped. The Indian Ocean Ridge volcanoes have never been comprehensively surveyed. The Mid-Atlantic Ridge has hidden segments beyond the famous Lost City hydrothermal field. The Bismarck Sea and the Bismarck Volcanic Arc contain multiple unverified active centers. The Aleutian submarine extension consists of chains of unmapped vents extending into Russian waters. The political dimension matters. Many unknown volcanoes sit in disputed maritime zones where access is restricted by overlapping territorial claims. The 2022 Hunga Tonga eruption demonstrated that even well-known volcanoes can surprise us catastrophically. The next Fani Maoré is probably already underway somewhere in the Pacific or Indian Ocean, undetected. Subduction zones, hotspots, and mid-ocean ridges each conceal different kinds of unknown systems. The Antarctic continental shelf submarine volcanic systems remain undermapped due to ice cover and remoteness. New mapping technology, including sail-drone autonomous vessels and large autonomous underwater vehicles, may transform the field within a decade, but 30% of the ocean floor is still mapped only at 5-kilometer resolution. The astonishing fact is that we have better maps of the far side of the moon than we do of the deep Pacific. The forward implication is straightforward. The next major submarine eruption will probably come from a volcano whose name does not yet appear on any list. 75% of all volcanic activity on Earth happens underwater. 80% of all eruptions in Earth's history occurred on the seafloor. Mid-ocean ridges taken together form the largest continuous volcanic structure in the solar system. Roughly 4 cubic kilometers of new lava emerge from the seabed each year, almost all of it invisible from the surface. The silence of the submarine eruption is an illusion of perception, not of physics. The 8 volcanoes in this video are samples from a much larger active population. The probability that one or more of them is erupting at low intensity at the moment you watch this is high. NW Rota 1 is erupting now. Fani Maoré is erupting now. Hunga Tonga is venting now. Kolumbo's chamber is filling now. Each volcano teaches a different lesson. Hunga Tonga showed that even a known volcano can surprise us catastrophically. Fani Maoré showed that continent-scale volcanism can happen unobserved for a year. Kolumbo demonstrated that monitoring is necessary, but not sufficient for prediction. NW Rota 1 revealed that some eruptions are not events, but continuous states. Marsili and Kikamjeni show that the tsunami is often the worst case, not the eruption column. West Mati and Monowai demonstrate that the seafloor is the most dynamic landscape on the planet. The cumulative warning is direct. Most coastal cities have never modeled their submarine volcanic exposure. The math is simple. 1.5 million seamounts on Earth, 10 to 100 eruptions per year somewhere on the seabed. The video's title is not hyperbole. By the time the credits roll, an eruption is statistically guaranteed to have occurred somewhere on the seabed. The closing thought is this. Every wave you have ever seen has rolled over an eruption somewhere. The ocean is not a covering. It is a window into the engine that built the planet. The question is not whether one of these 8 volcanoes will erupt. It is which one, and how soon, and whether the people standing on the coastline will know in time.